Okay. So last class we looked at the started looking at the 741 op amp, and we looked at the DC biasing scheme, right? We did the part of the DC biasing scheme for the first stage. Okay. So we'll continue with that. Hopefully finish that up for the second stage and the third stage, and then do the same thing for, do the small signal analysis. Okay. So just to quickly go over last class, so we started off building the 741 input stage, very similar to what we did for the MOS op amp, right? Started off with the differential path with the current mirror load, but then we figured out there are some problems. So we did two things. So first of all, we added the NPN, we removed the PNP current mirror. We added that as a common base configuration. Okay, so that is one thing we did. The other thing we did is we added some degeneration for the current mirror, right, to improve the output impedance. Okay, so we arrived at something like this. And finally, we also biased the gates of the NPNs Q3 and Q4 using an indirect biasing scheme, so that my input common mode can change and the bias voltage, the base bias voltage of those CMOSs will float with your input common mode, right? And then we started off assuming certain things. We assumed that the overall DC output voltage, now this will become more relevant when we start discussing the second and third stages, but we assume that the overall output DC is set to 0 by some feedback, overall feedback. We neglected NPN beta, but we couldn't neglect PNP beta, right? Okay, and then we found out the bias current. Finally, we found out that IC3 plus IC4 was approximately 19 microamps, right? So let me just copy this. Okay. So now we finished. Let's say we are done with the biasing for the first stage, right? So if IC3 plus IC4 is 19 microamps, you have 9.5 microamps through each side, right? So what do you think the second stage looks like? Actually, what do you think the second stage looks like? Similar to what we did for the MOSFET case, it's going to look like a common emitter, except in this particular case, you can actually use an NPN common emitter, because now the output DC level is somewhere VEE, it's plus a VBE, right? What is the output DC here? It's approximately, if everything is symmetric, it's going to be close to where this is, right? Maybe in this case plus 2 VBE, now that we have added the beta helper. Okay, but it's close to VE, that's what, it's close to minus 15 volts. So it makes more sense to use an NPN. So in this case, we are going to add a common emitter stage, except now let us say what we are going to do is, instead of adding a common emitter directly, we are going to add an emitter follower. So V into is VO1, the other reason for adding the emitter follower is because you need to take care of DC also, unless you want to use some AC coupling caps or something, right? Because that is actually at 2 VBE, right? We just discussed this. This point is at 1 VBE plus 2 VBE, right? So you need an emitter follower to change the DC. Is that right? Everybody sees that? Okay. I'm going to put this like this, a current source here. In a minute, we're going to look at what this current source looks like. What is not clear? What is the DC voltage at VO1? Yeah, sure. Okay, you're right. There is some resistor drop also. But what is the resistance drop actually? Actually, you can find out what the resistance drop is. 9.5 microamps times 1 kilo ohm. How much is that? So, few millivolts. It's not that significant compared to VBE. Right? Apart from that, you have VBE5 and VBE7. Right? So, it's approximately 2 VBEs above VE. Is that right? And the values of these, this is 50 kilo ohms and this is 100 ohms. Okay, I'll name these Q16 and Q17. Okay. This looks something like this, right? This part of the circuit. Something like 9.5 microamps. Okay? So I'm going to call this VB17. What is VB17? So, first of all, VB17 is nothing but VB17 plus, let me call this I2, okay, or why not, I2 times 100, correct? How is I2 generated? Now if you want to find out VB17 to find out the bias points and so on, you need to find out what I2 is. So if you remember, this particular, you have a diode connected transistor here whose current is pretty well known, right? So now what you're going to do is, you're going to take this guy, oh sorry, Q12, I'm looking at Q12. So if you see Q12, what is the current through Q12? We calculated this, can somebody look and tell? 733 microamps. Okay, so you're going to take this guy. So okay, you're going to create what is called a multi-collector transistor. I'm going to go back to the yesterday's class. Remember this donut layout? And we talked about separating out one side of the donut, right? Which means you could get 3/4 the current on one collector and 1/4 the current on the other collector, right? We talked about this yesterday. Okay, so that's what we're going to do in this case. Okay. What is this? Can somebody calculate and tell me? IREF is 733 microamps. What are I2 and I3? Approximately? This will be 183, right? Okay? And this is your I2 which you are going to use to bias the second stage. I3 will subsequently look, it's going to be used to bias the third stage. Okay? $550 microamps. So what is this? VBE is nothing but VT ln IC17 over IS17. Okay, so now we are getting to the point where we need to know some details about the circuit, right? Because why do we want to calculate VB17? Because that will help us calculate the bias current of Q16. Okay, right? Now you see that you actually need to know the details of what IS is, right? So what we'll do is we'll use a typical IS number. Now if it varies from this, obviously the bias points will vary a little bit, as much as maybe 20% from what we calculate. Okay, but it's a, we want to know the ballpark numbers. So we'll assume that the saturation current of the bipolar of the NPN is 10 power minus 14 amps. Okay. So can somebody calculate this and tell me? Of course, this is also 550 microamps. Point. Okay, so it's 695 microvolts. Sorry, millivolts. Okay, is that right? Huh? 0.697. Okay, so 0.697. Okay. Now the other thing we need to know this current. Okay. We'll assume a number of 250. Right. Now remember, these are all approximate numbers. Obviously betas will depend on process. Saturation current will also depend on the process. But we'll assume 250. What is IB17? .2 microamps. You can see it's a little bit large, right? Why did we start off calculating IB? Because the earlier stages were biased at very low currents, at 9 microamps or something. The actual currents are, base currents will be in nanoamps, so we can probably neglect them. Now these stages are now driving a second stage, which is actually having a bias current of 550 microamps, and you can see the base current is actually significant, right? What is IE16 now? I'm interested in this current. What is that? How did you find that out? It's VB7 over 50 kilo ohms plus IB17. Okay, what is that? (16.2 microamps). What is IB16? Oops, sorry. Again, I16 by beta plus 1 by 251. What is that? (64.8 nanoamps). Okay. So 64.8 nanoamps you can safely neglect with respect to 9.5 microamps. Right? This is the main reason for adding this emitter follower. Right? Because if you had added the common emitter directly, first of all, forget about the DC shift. Right? You would have had to take care of this base current somehow, supply this base current somehow. Right? Okay. Okay, so looks like now we have taken care of the second stage, DC at least. We'll start going through the gain and everything after this. What does the final last stage look like? Let me just call it the output stage. Okay, so you have taken care of two of the things, right? You wanted large gain, so you have taken care of large gain in the second stage. You wanted some large input impedance and so on, took care of that. What else do you need from the op-amp? Very small output impedance. We discussed that is one problem, because you might need to drive very low, very small loads, maybe even in tens of ohms. That's what I mean, right? If you remember when we were talking about driving resistances for the op-amp, in the case of the MOS, in the case of simple two-stage, that comes directly in parallel with R out and so on, right? Imagine if that were a few ohms. Even if your GM is very large, you won't get any gain at all. In this case, for the general purpose op-amp, you want to make sure that it can drive very small loads, maybe 50 ohms or 100 ohms. Okay? So what we'll do is, we will look at the output stage structure, just analyze it. More detailed analysis, we'll do it later, okay, after we get done, because we have not done output stages at all. I assume you have not done it before, right? Class A, Class AB, Class B stages? Probably not. After we get done with this and the differential op-amps, we'll come back to output stages as a completely separate topic, because that is actually a very fairly involved topic. It will require several classes. Okay? This is your I3, your 183 microamps. Everything. Okay, so this is what your output stage looks like. What is this? If you need very low output impedances, what do you usually do? If you need to drive very low output impedances, that means your output impedance of your op amp also needs to be very low. Right? How do you achieve that? Emitter follower gives you a very low output impedance. What is the output impedance? It's typically 1 over GM. Right? So you would use something like this. Okay, there are some more details to this which we'll analyze later. Again, we are actually neglecting some certain things. Okay, but this is a broad representation. And similarly later when we come to the output stages, we'll discuss why we have this, for example. Okay. But for now we'll just do the DC analysis. So this is the collector current IC23, and what is I out? 0, because we have assumed that overall DC feedback sets V out to be 0. Correct? DC wise. Okay? Is that clear? Oops. Okay, so now we'll start calculating, what are the bias currents of this guy, and so on. So now broadly what we'll assume is, so we'll start off assuming beta is very large, and now that we have started assuming beta is like 250 and so on, we'll have to check our assumption. For the first stage it was valid, second stage it wasn't valid because you have a pretty large base current. We'll start off by assuming beta is large, and then we'll verify, find out the base currents, find out the actual currents, find out if it is valid or not. Right? It's just VB 18 by 40 kilo ohms. That is the bias current of 19. Correct? So we'll assume, can you calculate VB 18? How do you calculate VB 18? Okay. Well, to calculate VB 18, you first need to know IC 18. You don't know that. Okay. So the easiest thing to do would be to assume, let us say, most of the 183 microamps flows through Q18. Okay. Find out VBE 18. Then you can calculate Q19. Find out if that's very large. So let's say this 183 microamps. If IC 19 was just a few microamps, that assumption is valid. Right? If it wasn't, then we have to go back and probably iterate. Okay, so can you calculate VB 18? Assume 10 power minus 14. So point? Okay, so .61. Okay, so what is IC 19? You will get something like 15.3 microamps. Is that right? Yeah, so right now we are going to assume betas are large, right? That's what I said. We'll start off by assuming betas are large. We'll go back and check our assumption. Right, we have not even, first of all, we have not even got to the point where there's actually multiple levels of iteration. Because right now we haven't even got IC18. Once we find out IC18, then we can find out, IB18. We aren't even there yet. Okay. So IC19 you get it to 15.3. So what is IC18? That is IC19. Now what is IC18? Yeah. It's just 183 minus, yeah, what is that? Something like 150? Sorry, 160? 167.7. Is that right? Okay. So now, of course, it's slightly different from the 183 you assumed at first. Okay, so use this 163 to recalculate IC19. Right? Find out what that is. Yeah, use 163 to find VBE and then go back to the same cycle. Yeah. What is it? Same means what? 15 point? You're getting same 15.3. So which means this distribution of current is correct. So you have 15.3 in 19 and whatever 167 in 167.7 in Q18. Okay? So these two values are correct. So no more iteration is required. Okay? So now the next step is to find out IC14 and 20. Right? How do you find that out? So there is one relation which is, so if you go from here to here, you have one VB like this. You have one more. So you can write a relation between the sums of the VBEs. Correct? Okay, let's just write that down. So VBE 19 plus VBE 18 is VBE 14 plus VEB 20. Okay? Okay? So now you can write it as VBE in terms of VT ln the current. Okay? What is this? Right? IC14 is the same as IC20. Right? Okay. So now you need even more detail to calculate the exact currents, because now you need to know the saturation currents of the different transistors. Now it's okay to assume 18 and 19 the saturation currents are the same, and similarly 14 and 20 saturation currents are the same. But what do you expect the ratio of the saturation currents? Do you expect them to be the same, different? What do you think? So you can assume 19 and 18 are the same, 14 and 20 are the same. Why is that? Actually, 14 and 20, can you assume them to be the same? You can't. Okay, so let's come to that, come back to that. Definitely 19 and 18 you can assume them to be the same. What do you think the IS for Q14 is going to look like compared to? Well, so far we have been assuming that all the saturation currents are the same. They are just, yeah, it's just for simplification purposes. So it is a fair assumption. We have been assuming it before, we can do that. What about 14 and, let's compare 14 because it's an NPN. What about 14? Do you expect that to be the same, larger, smaller? IS 14 will be larger. Why is that? Right? You're trying to drive a very, very large load, right, which is a very small resistance. So large load means large current, right? So now that means that most probably Q14 and Q20 are going to be large devices. And remember, your saturation current is proportional to the area of the device, right? So you expect Q14 and Q20 to be much larger compared to the other devices in your circuit. Okay? So now that will tell you. So let us say you can assume some certain number. Let us say we'll assume, let's say 3 times. Okay? Now that is again an assumption. So the idea is to get you to understand the operation and how you bias it, the approximate biasing scheme, right? So we'll put in this constraint, let us say. Okay? Then can you calculate IC14? $152. Is that right? Okay. So this is 152 microamps. Okay, so now you are done with the biasing, right? Now you have all 3 stages of the op-amp and you have taken care of biasing of all of them. Okay, now the next step is to look at the small signal picture, right? Let's start looking at that. By the way, what is IC23? We didn't calculate that yet. Huh? Why is that? Well, you are actually feeding a base current here, right? What is the bias current of this? 153 or 152, right? You need to know the beta of the PNP to actually calculate it. Now, why don't you take a representative number? What did I say yesterday? 40 or 50. See what happens if you have 50. What is the base current? 3, approximately 3 microamps. So what is this? 183. This is around 180, almost the same. Right? That's not a big problem. Okay, so DC biasing is clear to everyone? It's clear, right? In most cases we just followed some certain, very basic assumptions. Hopefully they are valid, but there are some assumptions which we made which may or may not be valid, right? Betas of the transistor, right? Beta of NPN, PNP, the saturation current or the area of the output stage. So those might change. So your actual answers could actually, be maybe 20-30% different, but that's still okay, because the whole idea of going through this was to get you to understand the structure first of all, how things are biased, and the approximate values of the bias current. Why do we need the bias current? Because we need to calculate the GM. We want the small signal, input resistance, output resistance, GM. For the bipolar, all of these things depend on the bias current, right? Yes. This one? Why did I put IS14 equals IS20? I just put it in there. Okay, in reality, like I said, it could be more. Well, it would be more, slightly more, definitely. Okay. Here for simplification purposes, I put it like this. Okay. So now to calculate the gain, we'll assume that it's being driven by a perfectly differential signal. What do you do with this side? If you assume a perfectly differential case, you can ground it. Okay? In reality, it is not perfect ground. There is still some, difference between the two sides, but we'll assume it's ground right now. Okay? Okay? Now, if you have two currents flowing in like this, okay, first of all, what all do we want to find? We want to find out GM, input resistance, output resistance. What do you do when you want to calculate GM? What have we done so far? Short the output, apply the input signal, calculate the signal current. Right? That's the easiest way. We want to calculate this current. Okay. Now we'll also assume what is the let us say here. So I'm going to call this Rx and Ry. Rx and Ry. What is Ry with respect to Rx? Actually, what is Ry? What is it? GM5 into 1K. Is that right? Okay, so GM5 into RO5 into 1K. Is that right? Okay, so what do you think it is going to be? What was here before we added this transistor? There was a short. What is the impedance when there was a short? 1 by GM. Right? After adding this transistor, what has changed in the signal sense? Okay, no, R pi, okay. What is the fundamental reason you got 1 over GM there? Because you are basically taking your collector signal and feeding it back to the base. Right? That's why you got the 1 over GM. What is the gain from the collector to the emitter here? Collector to the base here? 1. So do you think the impedance would have changed? Right? It will still be 1 over GM or very close to it. Okay? As long as, of course, we are assuming that the GM of this is very large and so on. Because in reality, remember, the gain of this is always never 1, it is close to 1. Right? Okay. What is Rx? Actually, I wrote down RY is much less than Rx, but what is Rx? It's what? Okay, this is the case where it looks like Cascode, right? We'll see, we'll get to it, but it looks like it should be large. That's what you expect. Okay? We'll calculate it. I'm going to make you next, if you have time, I'm going to make you calculate that. But the basic idea is RY is much less than Rx. Okay? So to simplify things for us, what we are going to do is, we are going to take this guy and to calculate the approximate gain, we are going to short this guy also to ground. Okay? Is that valid? Yeah. As long as this impedance is very small compared to this, right? If it's a couple of orders of magnitude smaller, it's definitely valid. Okay? So we're going to take this, short it to ground. So actually, what do we want here? We are interested in I out. Right? Is that right? Okay. So what is I out going to be? Can somebody calculate it? Not somebody, all of you calculate it. Not somebody. So now what can you do? First of all, now it looks perfectly differential. You can take the half circuit. Right? Okay. So now take the half circuit and calculate what I out is. I see some of you didn't bring your notebook. So what do? You take one half side, draw the equivalent circuit for that. Now for calculating the transconductance, neglect R out. That's what we've always done, even for the MOSFET. Right? That's the easiest way. When you're calculating transconductance, you short of the output, neglect R out. Right? When you want to calculate output impedances, you take R out into account. Right? What goes down here? So I'm going to call this V1 and V3. Correct? This is what it's going to look like. And you're interested in this current. Right? Okay, find out. So now remember, since it's a signal picture, you're not going to use the same beta NP and beta PNP, the DC betas. You're going to use beta naught, which is the signal beta. Okay? And you can simplify your answer. Assume that beta naught of both 1 and 3 are much greater than 1. Oh, by the way, there is one small detail I forgot to. Okay, one small detail I forgot to point out. Of course, what we are really interested in is this I out, and that is not exactly the same as just the I out on one side because of this current mirror. Okay, we'll come back to that. But why don't you calculate this I out first? I'm just going to call it. I'll just call it I3. Okay, or maybe IC3. Why don't you calculate IC3 first? We'll come back and see what I out is. Anybody? It's not that difficult, right? You have 4 components. Okay. So what do you have the answer in terms of? You have probably RPi1, RPi3, GM1, GM3 and so on. Well, you know RPi1 in terms of GM1 and RPi3 in terms of GM3. Right? And you also know that beta naught is much greater than 1. You can use those, beta naught 1 and 3. You can use those to simplify. First replace RPis in terms of GM, then apply the condition beta naught is much greater than 1. GM1, GM3 by times VID by 2. Okay, let's see. Let's see if somebody else comes up with the same answer and we'll confirm it. Right? GM1, GM3 over GM1 plus GM3 times VID by 2. Okay. So this is IC3. Can you tell me what V1 and V3 are? Actually, first we'll apply one. Before you do that, we'll apply one more constraint. Actually, is everyone on board with this? Let's wait for that first. Everyone is on board with this? GM1, GM3 by GM1 plus GM3, Amit? Okay. So we'll also, earlier we calculated the bias currents, we calculated the, base currents and so on, the collector and base currents. Now we'll assume that most of the collector current does flow through, because even though the beta is low for the PNP, most of it does flow through this. And since the collector, the currents are the same, we can assume that what is the GM of the device? IC by VT, right? If the same current flows, the GMs will be the same. So what is IC3? Okay, so it's GM1 VID by 2. Oh, sorry, by 4. What is V1? What are V1 and V3? Right, what is it? VID by 4, obviously, because if the GMs are equal, then you already know that is going, the VID by VID which you are applying here is going to split equally between all devices. Right, once you apply the constraint that GMs are equal, right, then the base emitter voltages are going to split, almost exactly between all 4 devices. So you apply VID here, VID by 4, VID by 4, VID by 4, VID by 4. Okay? I'll just put mod here. No, actually I think VID by 4. Okay? These are the base emitter voltages. Now what is I out? So now we have found out IC3 and IC4. What is I out? 2 times IC3. We have seen this before even in the MOSFET case. You have a current mirror. Right? So you have a signal here, and right? Remember you broke it into the half circuit. You analyze it for plus VID by 2. You have minus VID by 2, current is going to be flowing the other way. Right? So you're going to have twice the current. Okay? What is this? GM-VID by 2. Can you calculate what this is? What is IC1? 9.5 microamps. So calculate GM1 by 2. So what is capital GM? .183 you said? Okay, so yeah, so 180 milli, 180 microsiemens. Is that right? Okay, so now we have calculated one parameter. Then the next thing to do is calculate, let's say, input impedance. We will do that tomorrow, okay? We are already out of time today. So tomorrow we'll do input impedance, output impedance. So the final thing is to come up with some block diagram like this for the first stage, second stage, third stage. We'll multiply all the gains with the loading and so on. We'll calculate what the overall gain is, overall input impedance, output impedance and so on. Okay, that's the idea.